This training is Mid-Level System Design Part 2. It will cover pumping in parallel, series pumping, pump efficiency, the affinity laws, the effects of specific gravity and viscosity, and pump curves and pump selection. Parallel pumping is when two or more pumps are pumping from the same source into a common pipe or header, or sometimes just discharging into open atmosphere. This setup is primarily used for variable flow operations. The system can adapt to variable flow by adding or subtracting the active pumps in order to achieve the desired flow, while allowing the pumps to perform at near peak efficiency. If a system has two identical pumps, the head will remain the same as if you had a single pump, but it will produce 2 times the flow. If the system is pumping into a common pipe, make sure it is large enough to handle the maximum possible flow without exceeding the total head of the pump due to friction losses. Series pumping is like parallel pumping, but produces the opposite result. Pumping in series is designed to achieve higher heads at the same flow rate. The first pump is set up normally, but its discharge is piped directly into the suction of an identical pump. If the pumps have the same hydraulic characteristics, the head is doubled at a given flow. It's important to know that the pressure a pump sees at the suction is not lost or destroyed as it goes through the pump. That initial pressure is added to the differential pressure the pump creates. This means that the second pump in series will see much higher pressures than the first. Be sure that the second stage pump can handle these pressures. Typical modifications to allow for higher pressure operations are class 300 flanges, a balanced mechanical seal, and the removal of the priming systems, which are not designed to handle high pressure. Recall that normal suction pressure are low or even a vacuum relative to atmospheric pressure. Pumping in series generally requires less horsepower compared to running a larger pump at the same duty point. Pumps can be ran at higher efficiencies in most cases and at lower speeds, which reduces wear, uses less energy, and increases the pump's working life. Pump efficiency is a major selling point and pivotal characteristic of the pump. It's easy to read the efficiency off the pump curve, but it's important to understand where this number comes from and what it means. Pump efficiency is the power of the water divided by the power of the shaft. It is a percentage of how much of the shaft power is being transmitted into the fluid. The power of the water or fluid is determined by multiplying flow in GPM by head, which is in feet. This number is then divided by 3960 to convert it to horsepower. Once water power is calculated, it is divided by the brake horsepower of the shaft to get pump efficiency. Underneath these numbers lies 3 main factors in determining overall pump efficiency. The first factor is mechanical efficiency. Mechanical efficiency includes friction losses in the bearings and seals. While modern ball bearings and cassette seals have low friction losses, they still negatively affect efficiency. The second factor is volumetric efficiency. This includes any leaking or recirculation of the fluid. Volute design, modern seals, O-rings, and tight wear ring clearances all help decrease these effects, but most all pumps have some leaking or recirculation happening during operation. The third and largest factor in pump efficiency is hydraulic efficiency. This includes liquid friction and losses in the volute and impeller. A well-designed impeller imparts more of the shaft power into the liquid. Enclosed impellers, like Pioneer uses, prevents more recirculation compared to semi-open or open impellers. The affinity laws relate to performance of centrifugal pumps. They help extrapolate and predict pump performance at different velocities and impeller sizes. They are most useful for when a pump needs modified to hit a different required duty point. The speed change laws help predict flow, head, horsepower, and even NPSHR at a new given speed. Let's say a pump curve only goes up to 1800 RPM, but the customer wants to run it at 2200 RPM to see how much more flow they can get. The first equation can predict that flow. Before we move on to cover diameter changes in relation to the affinity laws, let's run through a speed change example. The initial operating condition is 100 feet of head at 2,000 gallons per minute, running at 1800 RPM. We want to know the change in head when the speed is increased to 1950 RPM. Step 1 would be to use the head equation to calculate head at the new speed. After we plug in the figures, the resulting head value is 117.4 feet. Be aware that this new head value also has a new flow rate coupled with it. You cannot increase the speed of a fixed system and not also increase the flow. To find the new flow rate, simply plug the speed values into the flow equation. The new flow rate at 1950 RPM comes to 2167 gallons per minute. The images shown are curves generated from our pump flow software, confirming that our math is correct. The affinity laws for diameter changes works the very same way. Trimming the impeller is a common practice when trying to hit a specified duty point within the limits of a specific horsepower or max speed. An example would be a customer is sizing a pump, but he only has a 20 horsepower motor. The plant requires a certain size pump, but the pump at full trim overloads the motor by requiring 30 horsepower. By trimming down the impeller, the horsepower required will be reduced. One way to solve this problem is to solve for the new diameter, diameter 1, when the desired horsepower is 20. This involves some equation manipulation that could be a little confusing, so another option would be to guess and check. Let's say the full diameter impeller is 10 inches, which is our diameter 1, and we want the required horsepower if we trim it down to 8.5 inches, diameter 2. When we plug these numbers in and solve the equation with the initial horsepower being 30, the new required horsepower is 18.4. This new trim will not overload the 20 horsepower motor. It's important to understand that while the affinity laws are useful and can be fairly accurate, they do have strict limitations. Notice that affinity laws for diameter change do not predict NPSHR. The affinity laws are not valid for changes greater than 10% for both speed and diameter. And lastly, the laws assume stable operation, meaning no cavitation or recirculation, and that the system has remained constant in terms of pipe size and lengths. Specific gravity is defined as the ratio of the density of a substance to the density of a standard substance. This is usually water for a liquid and air for gas. Surprisingly, it has no adverse effects on pump performance, but it does affect horsepower required. This can be proven by using two different equations. The first equation is used to calculate brake horsepower. Because specific gravity is a required variable, it directly affects brake horsepower. The heavier the fluid, the more horsepower required. The second equation is used to calculate work done by the pump. This equation considers the weight of the fluid in pounds per gallon. If a given fluid weighs more than water, the amount of work is increased, thus increasing required horsepower. Unlike specific gravity, viscosity can greatly affect the pump's performance as well as power required. Correction factors need to be applied to the pump curve once viscosity reaches 30 to 40 centipoise. It has little effect on NPSHR, but it greatly reduces NPSHA. Due to the increased required horsepower, be mindful of the torque and horsepower limits of the pump shaft. The viscosity limit for centrifugal pumps depends on the application, fluid, and pump geometry, but they can vary from 250 to 1000 centipoise. It is recommended to work with the pump manufacturer if the fluid is over 250 centipoise. The curve shown is a standard various speed curve for the Pioneer Prime 66S12 trimmed to 11 inches. There are many lines and figures displayed on the curve, and they are all very important to understand. Let's first establish our X and Y axis. The X axis is always flow, either in gallons per minute or the metric meters cubed per hour. The Y axis represents head, either in feet or meters. Depending on how and where the curve was created, there might be a shaded region in the middle of the curve which represents the POR, or preferred operating range. This range is commonly defined as 70 to 120% BEP, which stands for best efficiency point. Towards the top there is a blue dotted line labeled NPSHR at 1800 RPM. At a given speed, NPSHR only varies with flow. To find NPSHR at a given flow, simply find the flow on the x-axis, follow that point vertically till you reach the NPSHR line. At that point, draw a line over to the right and read off the chart running from 0 to 35 feet. The more vertical and curved lines on the graph are the ISO efficiency lines. These lines tell you what the pump efficiency is anywhere on the curve. Each speed curve has a best efficiency point. That point is where the speed curve intersects the highest efficiency line. The other dotted lines shown in the curve are constant horsepower lines. When sizing the motor for any application, an important consideration is whether the pump will ever be required to operate at a flow rate higher than the design point. If, for example, the pump could operate at the end of the head capacity curve, the actual horsepower requirement may exceed the design point selected motor horsepower and overload the motor. For this reason, it is common practice to size the motor not for the design point, but for the end of the curve or maximum horsepower requirements. The last two terms commonly brought up with pump curves are shutoff head and runout flow. Shutoff head refers to the maximum head value at zero flow. For this pump, it is just under 200 feet. Runout refers to the maximum flow for any of the speed curves. This pump would be about 2,800 gallons per minute. The image shown is a screenshot of the pump curve of the PP66S12 trimmed to 11 inches when putting in the duty point of 1,500 gallons per minute at 120 feet. Pioneer uses two different pieces of software for pump selection, PumpFlow and Intelequip. The software used for this slide is PumpFlow. As mentioned in part 1 of this training, the pump will operate where the pump curve intersects the system curve. Because our trim is fixed, PumpFlow calculates that the speed needed to hit this duty point is 1990 RPM. PumpFlow also calculates NPSHR, efficiency, and power required at the specified duty point. The next step in the selection process is knowing what the driver is and making sure it can hit the duty point. If the driver is a diesel engine running at 1990 RPM, shouldn't be an issue, being that most diesel engines can run at that speed. However, if the driver is an electric motor, a problem arises because 1990 RPM is not a nominal motor speed. Luckily, there are a few options for hitting the required speed. One option is a variable frequency drive, or VFD, that can speed up the motor like the throttle to an engine. The other option is to belt drive the pump. Running belts allows for the pump to be ran at a higher or lower speed than the nominal motor speed by utilizing belts and pulley ratios. Another scenario is that the speed is fixed and we need to hit a specified duty point. This is where we utilize a various trim curve and figure out what trim is required to hit the duty point and not exceed another potential limiting factor like horsepower. PumpFlow provides all the variables we need to calculate efficiency. Let's use the formula given earlier to double check the 67.7%. The equation was power of the water divided by the power of the shaft. The power of the water is flow, which is 1,500 gallons per minute, multiplied by head, which is 120 feet, and then divided by 3960. This totals 45.45. When we divide 45.45 by the brake horsepower of 66.9, the efficiency comes to 67.9%. This is very close to the 67.7 that PumpFlow calculates. This concludes part 2 of mid-level system design. To review, this training covered parallel pumping, series pumping, pump efficiency, the affinity laws, specific gravity and viscosity, and finally pump curves and selection. Thank you for watching, and feel free to contact Pioneer Pump directly if you have any questions about this training or future videos.